Hello and welcome everyone. Still some people dropping in. Find a seat, there's plenty left. So welcome to my talk where I'll give you an introduction and tell you all about the pitfalls of Java's new concurrency model. My name is David Vlijmincx. I'm a Java developer in the Netherlands. Been developing Java for around 8 years now. You can find me on Twitter or at my website. I'm happy to engage. And since this week I'm also an Oracle ace, which means that I like to talk a lot on stage. So, as you all know, questions you can ask them using Slido. So just visit the website, fill in the code. The room is room 9. So if you don't know already, we're going to talk about virtual threads. So if you have any questions, feel free to ask. There are no stupid questions, and I like to answer all of them. So today, what I'm going to talk about, I will start with the current situation. What are the threads we are using today, or well, previous year really, or before September to be very precise. And then I will show you what are some of the limitations, how are we using these threads that we currently have. And then I will slowly talk about virtual threads, why they are so great, and at what use cases they really excel at. And then during the demo I will show you how you can create lots of virtual threads. And when you have lots of virtual threads, you also have lots of lifetimes you have to manage. And that's where structured concurrency comes in. And that will help you managing all the threads that you'll have. And at the end, there is some time for a Q&A. So, platform threads. So, who has created a thread like this before? That's really a lot of people. That's really great. Who has, by the way, already played with virtual threads? Still some more hands. That's also great. Cool. So what happens here is that we have a thread class. We're going to create a thread inside our application. And when we call this thread constructor, we are going to ask the JVM, can you create a thread for me? And we are going to create a thread. And then we have to go to the operating system. And then we ask the operating system, can you create a thread that I can use inside my application? Because a thread inside Java is just a very thin wrapper around a thread that is managed and scheduled by the operating system. So when we create a new thread, each time we have to go to the operating system. It has to allocate around a megabyte of memory for each thread that we're going to create. And then we have a thread inside Java that we can use. And then we can pass the task, and if you call start, it will start running that task. So that's really the basics of the threads that we currently have. And as you can see, hinted at the top, it says platform threads. That's because now with Java 21, there are now two kinds of threads we can use. The platform threads, or the virtual threads, that I will talk about later. And we call these threads platform threads because they are managed and scheduled by the operating system. So to be able to tell them apart, these are now the platform threads and the virtual threads. Well, they come later. So how can we use these platform threads? Well, the most easiest way for us developers is to create a thread for every task that we have. So here I have 3 tasks, and for every task, I create just a thread right then and there when I need to. And while this is a very easy way for us developers to create concurrent code, because every time I just, where I am in my method, I can just create a thread, and it will start executing this task. And then when it's done, it will be discarded, and the garbage collector, well, it will clean it up for me. Which is all very nice, but we don't use the resources that are available to us in the most optimal way. Because every time we have to go to the operating system, it has to allocate some memory, which will cost memory and some time, and then only to be discarded when the task is done. So creating a thread for each task that we have is a very nice way of developing, but it doesn't make best use of the resources. So how can we solve this? With Java 5, or since Java 5, we are encouraged to use the executor services instead of the thread class directly. So here I have my little box. It's an executor service, and it has 3 threads that can perform tasks. And I can just submit my tasks. They will be put in the queue, and then my executor service will start executing each task as they come along. So every time I submit a task, a thread that is available, it will pick up the task, it will start running it, and when it's done with that task, it will be put back inside the pool, and it will pick up a new task to run. So now we are making better use of the resources because we are not creating threads only to discard them a few moments later, but we are now reusing them, which is really great. But that also comes at some cost that we have to look out for. For example, if your thread isn't doing anything, so let me rephrase that. So, imagine you have a thread that is making a call to a database and has to wait for the answer to come back, for a result to come back from the database. In the meantime, that thread is blocked. It isn't doing anything. It isn't picking up a new task to run. So at that moment, you have just a thread doing nothing. It's just waiting there while it could do better stuff. And of course, you have the leaking of thread local variables. If, for example, I have a task that sets a thread local variable on one of these threads but forgets to unset it, when that thread is put back inside the pool, other tasks that run on that same thread are able to read those thread local variables. So at that time, you're leaking your thread local variables from one task into another, which isn't really great. So while the executor service makes better use of the resources, and still quite an easy way for us developers to use them, there are still some ways it can be improved on. And one of those things is with async programming, which is also a very good way to make use of the resources that are available to us. Because async programming, it's, in my opinion, very hard to write. It's even harder to read, especially 2 weeks after you wrote it. And it is also hard to debug, because the Java, the JVM, is really made around threads and stack frames. And with async, that kind of goes out the door, and that makes debugging just a little bit more difficult. And of course, the callback hell, if you are familiar with that, that's also not the most pleasant experience, especially if you have to read that. So let's talk about virtual threads. And virtual threads are just an alternative implementation of the thread class. So the old threads, the threads that we were using before Java 21, they aren't going anywhere, but we just get a new flavor of threads we can use. And those are the virtual threads. And the great thing about virtual threads is that the operating system doesn't know anything about them. They are just a concept that lives inside the JVM. So when I create a virtual thread, I don't have to go to my operating system and ask it to create a thread for me. I can just stay safe inside my application. And it does have some benefits. For example, if I want to create a virtual thread, I can just allocate a very tiny amount of memory in the heap for that virtual thread. So it can just start out with just a few bytes. And as the stack frames grow of this virtual thread, so will its size on the heap. It will just resize it so it can use up more space. And of course, when the virtual thread shrinks in size, then it will also use less space on the heap. So, and that's just really a great thing, because then the virtual thread uses a lot less memory from the start, and it doesn't waste anything, because memory is still a precious resource. So because they're very fast to create and they don't use a lot of memory, we consider these virtual threads to be very cheap. So I made 2 applications, one that uses virtual threads and one that uses platform threads, to show you how cheap those virtual threads are. And as you can see, at the bottom I have the number of threads, and when I created the application with 1 thread or 10 or 100, you can see that it doesn't change a whole lot in the memory usage. They still are quite similar. The platform threads are even using less memory in the beginning, when you're still using 1 or 10 threads. So then it's a better idea to still use platform threads. You don't gain that much. But if you go into the larger numbers, you can see that virtual threads really start to make sense. Because as you can see, with 10,000 platform threads, my memory usage starts to skyrocket. It's almost at the top of the graph. And as you can see, with 100,000 threads, I couldn't even create 100,000 platform threads because it ran out of memory. So that problem kind of solves itself. And then I have the 100,000 virtual threads that will just use a little bit over 250 megabytes of memory, or close to. So as you can see, with virtual threads, I can create an application that uses as many threads that I would like to use. So that's enough of the slides for now. So let's switch over to the demo. So here I have, is it all readable for everyone in the back? And no complaints. So So let's start. So as I've said, you can create a virtual thread. They are just an alternative implementation of the thread class. So I can just still use the thread class to store a reference to it. So let's create a virtual thread. And to do that, I have to call this static builder method called start virtual thread. And I can just pass it a task that I would like for example, the print task. And call vt.join to give the thread a chance to print something to the console. So what start virtual thread really does is that it will create a virtual thread for me to use. And it will start this thread immediately with the task that it has been given. And as you can see, it prints hello everyone to the console, which is really great. So you have officially been greeted by a virtual thread. So that's one way of creating a thread, or of a virtual thread to be precise. The other way is with the builder method called off-virtual. There's also a off-platform, which will create platform threads, but with off-virtual, you will create a virtual thread. And with the builder, you can set some things like, for example, the name. I'm going to call it vd thread. And I can give it a unstarted task, which is also going to be the print task. And with an unstarted task, the thing I have to do is start it myself. And then when I run this code, it should do exactly the same, but now I built a virtual thread using the static builder method. No, using the builder method. And it prints hello everyone. So that's really great. So now we can create a virtual thread using the thread class, but since Java 5, you are encouraged to use the executor service. So with Java 21, we also get the executor service that uses virtual threads. And it's called the new virtual thread per task executor. Well, which, as the name just does imply, we will create a new virtual thread for each task that has been submitted. And as you can see, IntelliJ makes this yellow, which means there is something to be improved on, which is correct. And that is with Java 21, the executor services now implement the auto-closable interface, which means that I can use it inside a try with resource statement. So now I can do stuff like this. And print things 3 times to the console, which, as you will see when this finishes, it prints hello everyone to the console. And the great thing about this is that I don't have to call join anymore on those virtual threads. Oh, someone is getting a very close-up picture. That's cool. So as you can see, it prints hello everyone 3 times to the console. And the great thing about this is that I don't have to call join on those virtual threads anymore. Because when I exit this try, all the virtual threads that I have created either will be finished successfully or unsuccessfully. But either way, before I exit this try, all my virtual threads are done one way or another, which is really great. So let's do something a little bit more exciting and create a lot of virtual threads. So let's create 100,000 or 10,000 of them. That would be taking a little bit too long. Submit. So what I'm going to do here is I have a for loop. I'm going to go over it 10,000 times, and I'm going to submit 10,000 times the sleep 1 second task, which will create 10,000 threads, which will sleep for just a single second. So I'm going to let this run for a bit. Shouldn't take very long. And there you go. There you have it. I just created 10,000 threads that all slept for a second and then continued. Well, it isn't the most exciting example. It shows you that on even a laptop, I could create 10,000 virtual threads without getting an out-of-memory exception. Because creating 10,000 platform threads, well, takes up a bit of memory. So that isn't ideal. So let's see how this all works behind the scenes. Because what I just did is that I created 10,000 virtual threads, but as this is a laptop, it doesn't have 10,000 cores. So how do these virtual threads actually run? So here I have a bunch of virtual threads. And let's say I have a system with 4 cores. How does this map 1-to-1? Because how do these virtual threads get some time to execute their code? And a virtual thread doesn't run directly on a core, so to speak, but it runs on a carrier thread. And a carrier thread is nothing more than just a platform thread designed to run or to execute virtual threads. So every carrier thread gets one virtual thread to run. So how does it work? So what I did was create 10,000 virtual threads, and each of those virtual threads will be picked up by a carrier thread. So here I have a bunch of carrier threads. Each will pick up a virtual thread from a queue to execute. And those carrier threads will, of course, behind the scenes run on some thread managed by the operating system. So by default, you will get as many carrier threads as there are cores available inside your system. But there are ways to limit that number or to change it if you want. Using the parallelism parameter, you can say how many carrier threads you want to be created once you start up the application. So for example, with 5, I would have 5 carrier threads during the lifetime of my application, instead of the default, which will be the cores available inside your system. And as you can see, there's also a second parameter that you could change, the max pool size. There are some use cases where the GVM will create extra carrier threads if your platform thread gets blocked. And using the max pool size, you can limit that number of how many extra carrier threads get created. So how does a carrier thread know when to switch from one virtual thread to another? Because I have this carrier thread, it's running a virtual thread. How does it know when to switch? And when a virtual thread gets blocked, it will be unmounted. So this virtual thread will continue running. It will stay put on this carrier thread until it encounters a blocking method. And when it does, it will be taken off this carrier thread and put back inside the heap. So the entire stack frame of this virtual thread will be copied from the carrier thread back into the heap. So that the carrier thread is now available for a new virtual thread. And so what will happen is that the old virtual thread is taken off, and a new virtual thread will be mounted into the carrier thread. So the carrier thread will pick up a new virtual thread from the queue and start running that instead. And this cycle will continue. Each time you have encountered a blocking method, the virtual thread is taken off, and a new virtual thread will take its place. So as you can see, I really have this life cycle in a complete picture. But not every blocking method is ready yet. So as you just saw, here I have the life cycle. So every time it's blocked, it is put back inside the heap, back inside this queue. But it doesn't happen every time. So let's go over some more of the pitfalls of virtual threads. So for example, the synchronized block. If you enter a synchronized block or an object.wait, or make a call to a native code using something like GNI, or even certain file operations cause the virtual thread to be pinned to its carrier thread. And pinning means that the virtual thread can't be taken off the carrier thread. So it will be stuck there, and then you lose one of the biggest benefits of using virtual threads. So if your code base uses any of these methods together with virtual threads, is something to look out for and see if you have any performance issues while running those methods. So how do you detect if a virtual thread is pinned? There are 2 run options, it's a run option and a system property that you can use. And you can specify if you want to have a short description or the full description, and it will show you the places where the virtual thread gets pinned with a line number and everything. So if you add this as a run option to your application, it will print out where the application or the virtual thread is being pinned. And you can see if it happens a lot. If it doesn't happen a lot, it probably isn't a problem. But if it happens quite often, then you might want to change that part of the code. So some of the pitfalls of virtual threads is that they aren't any faster than just platform threads, because the virtual thread still runs on a platform thread. And because it only works very well when they have blocking methods, so when they are blocked, they can be taken off. If you're using them for long-running calculations, your virtual thread will never block so it will be stuck on the carrier thread. So you can never have the switching, the mounting and unmounting part. So don't use it for long-running calculations, because it could impact your performance. And of course, you don't want to pull your virtual threads, because they are so cheap to create, the virtual threads, that you really just want to create them when you need to, and discard them when they are done. They are really that cheap. So pulling them is really becoming an anti-pattern. And of course, some old libraries may still use the unsupported methods. So that's also something you have to watch out for. So let's go into the second part of this presentation, and that's structured concurrency. Who already has played with structured concurrency before? Some hands, that's really great. So as some of you might know, this is still a preview feature. Some things might still change, but the ideas behind them will hopefully stay the same. But some of the API calls may change. But it's a very nice feature about managing the lifetime of your threads. So before I dive deep into what structured concurrency is about, let's take a look at a simple example first and dive deeper in from there. So this is an example of structured code. And this is just a very simple method called method A. It calls two methods, method B and method C, and it creates a result of these two methods. And the great thing about structured code is that it really shows you the lifetime of what happens inside method A. So here on the right, the lifetime of method A is at the bottom, and inside method A I'm going to make a call to B and C, and after that I will have a result that I can return, which is all really nice. And the great thing about structured code is that it really shows you the relationship between these methods. So when something happens, for example, method B throws an exception, I know that I can stop my method right then and there. I don't have to call method C anymore. I'm not going to try and create a result because it doesn't make any sense. And I can just rethrow the error to the parent, and all will be nice. I don't have to do anything more myself. And of course, the same goes for method C. If that throws an exception, I will stop the method right there, and the program can handle it from there on. So when I do this with threads, I really create an implicit relationship between them, because here I have again the same method, method A, but now method B and C use something of concurrency to run to get their result, and I will just wait till my method A to the result is till I can create the result that I want. So here I have method B and C. They run concurrently. B takes a little bit longer than C, and then after it I can just create a result. So what now happens if I have an exception, for example in method B, I have kicked off method B, it will run for a few seconds and counter an exception, but method C will continue running. It doesn't know anything about method B, and it will run until it's done. And inside method A, when I get at the foo.get, I know that my application or the thread inside method B is, well, threw an exception because I can't get a result from it. And I can just stop right there. But when I'm at this return part, at the return line, then I find out that my method B just has stopped. But then I have to stop my thread inside method C. So I have to go out of my way to stop that thread from running, because it will just run until the result is created, which is unnecessary because I can't create the result that I wanted. And the same, of course, happens when method C throws an exception, but it's a bit worse because, well, method B takes quite a long time to run. And as you can see, at the foo.get, I will have to wait till method B is finished. Method C has thrown an exception in the meantime. So when method C threw an exception, I can really just stop that code. I wouldn't have to wait for the method B to stop or to give me a result, to return me a result for me to continue. So then it could just have stopped. And the same thing, of course, goes when the parent thread dies. I have two threads running loose inside my system that I just have to know about, that I just have to stop. And I'm not mostly not looking that close to the exceptions happening. So if it even threw an exception. So then you have to stop two threads all by yourself. And structured concurrency really makes this part a lot easier, which I'm going to show you with a demo. So here I have the way Java implemented the destructured concurrency part. And the thing I want you to focus on is that it all happens inside this try with resource statement. As you can see, structured concurrency inside Java is implemented using the structured task scope. Any structured task scope has 2 built-in shutdown policies, and a shutdown policy states when the relationship between the virtual threads that I'm going to create. So in this example, I have the shutdown on success, which states that whichever virtual thread finishes first will be the winner, and the rest will be cancelled. So every thread that I'm going to create is going to run, and when the first one has finished, I will shut down the rest, or the structured task scope will shut down the remaining virtual threads. And I tell Java that, or my application, that the value that is going to be returned by my virtual threads will be of type string. So inside my try with resource statement, I fork 2 new threads, 2 new virtual threads from the scope I just created. These virtual threads will start running immediately, and they will return result 1 or result 2 for the second virtual thread. And then I call a scope.join. And at the scope.join, my parent thread, so the one running the main method, will block, and it will wait for my shutdown policy to be finished. So it will wait till either of those threads has finished, and then I can continue. And then with the scope.result, I can get the result of the first thread that has finished. So I don't have to check each of my virtual threads, but using the scope object, I can just get the result immediately. So when I run this example, you can see that the first thread finished first and it printed result 1 to the console. So either thread, the second virtual thread either finished successfully but was ignored, or if it was still running, it would have been shut down, because I'm only caring about the first virtual thread to finish. So there are, as I've said, there are 2 built-in shutdown policies, and the other one is the shutdown on failure. And the shutdown on failure policy states that all the virtual threads have to finish successfully, or if one of them throws an exception, I will shut down the rest of the remaining virtual threads. So again, I create a new structured task scope beside the try with resource statement. And here I fork 2 new virtual threads. Again, they will return a result 1 or result 2. And I will get a subtask. And the subtask I can later use to fetch the result that I want from those virtual threads. And to make this example a bit more interesting, I use, again, a scope.join, but I gave the virtual threads a deadline. With the join until, I say that the virtual threads have 10 seconds to finish. If they don't finish in time, I will the structured task scope will shut them down. If they finish in time, it will just continue. And then I have another interesting part, and that's the throw if failed. So after the virtual threads have finished, either successfully or unsuccessfully, because one of them threw an exception, I can rethrow the exception using the throw if failed, and it will rethrow the exception of the virtual thread. So after the join and after the throw if failed, when I get into this print line, I will know that my virtual threads have finished successfully, both of them, because it didn't throw an exception, and I continued from the scope.join. So knowing that, I can just use the subtask and the .get method, and it will return the result of those virtual threads, because they must have finished successfully. So with structured concurrency, with Java 21, you get 2 structured task scope shutdown policies by default. But sometimes you want to create something your own that's a little bit more, that fits your use case a bit better. So what I wanted was a structured task scope that shuts down when it finds me a product that's worth less than 100. So I'm going to look for a product that's worth less than 100. So I created these 3 methods, the get the product of 50, one of 300, and one of 200. And I will give these tasks, these methods, I will pass them to a virtual thread, and they can get that product for me. And the structured task scope will know when the product is less than 50, then it can shut down. So let's see how you can implement something like this. So to create your own structured task scope, you have to extend the structured task scope class. So I called mine the criteria scope, and the criteria is, of course, find a product less than 100. And then it's very important that you override the handle on complete, because the handle on complete is going to be called by every virtual thread. And because of that, I want to check two things. Did the virtual thread finish successfully? Didn't it throw an exception? So when it finished successfully, it means that it has found a product. And the second thing, of course, is the product worth less than 100? And if it is, if both of those statements are true, I want to get the product from that virtual thread and shut down. I'm not going to shut down the whole application, but just the structured task scope. So the shutdown will cancel all the virtual threads that are still running. And then I can fetch the results using the getResult method. So running the own criteria scope is very easy. Again, create a try with resource statement. I create my new criteria scope. It already knows the type is product. And then again, with the fork method, I'm going to create 3 new virtual threads that each are going to fetch the products that I want. And then again, a scope.join to block until a product has been found or all the virtual threads are finished. So when I run this example, it prints out that the product worth 50 was successful. 300 came in a little too late, so it was cancelled. So it's unavailable. But as you can also see that the product, the virtual thread that was searching for a product with that's worth 200, it did finish successfully. So in the handle on complete, it did finish. It did call that method. It was successful. But we also checked that the product was worth less than 100. So it still finished successfully, but it didn't shut down the structured task scope. And of course, to show you that it actually works, I printed that the found product with the structured task scope is printed to the console. So what it did was, it was searching for 3 products, and when it found something worth less than 100, it shut down the structured task scope, and using the scope object, I could get the result. So the pitfall is really managing the lifetime of threads yourself. The structured concurrency part really makes the relationship between your threads very explicit, which makes it easier for other developers to know what you want to do with those virtual threads. If one of them throws an exception or doesn't find any result, it really helps show you what the relationship is between those threads. So most of you already played with virtual threads, but the ones who didn't, it's very easy. You just need these 2 methods, the start virtual thread or the new virtual thread per task executor, and you can start playing with virtual threads yourself. So the API didn't change a whole lot, but virtual threads are still very powerful. So thank you, and then I'm going to switch to the Slido. Will reactive programming finally die? A very nice question. I hope so. Yeah, it's not my favorite. I'm going to admit that, but yeah, I hope that virtual threads will take over the world. Can virtual threads thread local storage? I know that there are scoped values, so you can use that instead. So I'm going to say yes, but use the thread local scoped values instead of the thread local variables. You show that virtual threads consume less memory than platform threads. What about stack? If there is a lot of nested method calls, do virtual threads need less memory to store the stack? Then that's a very good question. I think it will use the same size, but I'm not sure yet, because I have to look it up. But yeah, it would be weird if it uses less memory, but I don't know. I have to look it up. Can virtual threads be preempted? That's where my English struggles. What does preempted mean? Oh, that's a very good question. I would guess that that's That's a very good question. I never tried it because all the virtual threads never threw an exception, but I would guess that the virtual thread will just put back aside the queue and will be picked up later again, but I would have to test it out. Sorry? Are any modern web servers already using virtual threads? Well, there is this Helidon thing, which is a really great, really great framework. So I would really check it out. It's the Helidon Nema part, so do look it up. It's really nice. Why not use virtual threads for long computations? You can, but you won't see much of the benefit. That's really the thing. You can use it, but because you will never block, the virtual thread will never be taken off. So another virtual thread can't take its place. And virtual threads are really just good at being blocked, just waiting for a result to come back. And with long-run calculations, you could just use the platform threads, because you then also don't have the overhead that the virtual threads have. So I hope that answers that question. Why are scoped class names so long? Yeah, because they are, are static classes inside the, why not look it up? Because when I go to this, the class name is also very long. It's the imports. Very long. So they are, because they are inside another class, so you have the class and the child, and then you have to go to the entire structure. But you can create your own, and then the names can be very short, so even just one letter. So, is it a good idea to use virtual threads to implement waiting for some resource in the REST call? If it's not good for, yes, that's a very good use case, because during the REST call, it's just being blocked. It will be taken off the carrier thread, and when the result is coming back, the virtual thread will just continue with the answer from the REST call. So yeah, it's a very good use case. Because the long computation part really is about the virtual thread waiting. You don't want to have the virtual thread running for too long, and then it can be taken off, and then you get the point. Calling the shutdown in the for demo is necessary. What if we don't? I would guess it will never shut down and just wait for all the virtual threads to be done. But yeah, let's just do it. So yeah, let's see what it does. So as you see, you don't have to call the shutdown method yourself, but you can still do it. So yeah, that's nice. Calling the how would one test code which uses virtual threads? I would guess you would do it the same as you would with the platform threads. Or is there something specific you want to test with the virtual threads? I don't know, ask the question, or you can always ask a new one on Slido and then it will pop up. Can you allocate more carrier threads than OS threads? How do they share the resources then? Yes, you can, using the parallelism parameter. If, for example, you have a 4-core system. If I put this to 5, I have 1 carrier thread more than threads, and then normally than the cores that are available. So more platform carrier threads than I would have by default. And then the resource sharing is really just up to the operating system, because it's still the platform threads that they are running on. So I would guess the operating system is still handling those resource management. What about stream of virtual threads, which is a nice API? I think there is some. What about streams of virtual threads? There is some part with the structured concurrency part, where they want to use a stream of virtual threads. So there is some talk about that on the mailing list, but it's not in the preview version just yet. But it would be a really nice API, that's for sure. Will I gain anything by virtual threads without using them explicitly when using some framework? Yeah, you can still, for example, if you have a lot of blocking calls, and Spring will somehow magically know, but of course, when that happens, you can just have more threads running concurrently, being blocked concurrently. So, for example, doing queries to a database. So, yeah, you will gain more concurrent. You can have more concurrent threads than you could have before. So, yeah, you will gain certainly some performance. Second demo, how are the threads stopped? It's hard to stop running threads and not using. How are the threads stopped? I'm not sure. I would have to look at the source, but because that's the second demo. Shutdown on success here. Yeah, then we would probably have to look through the whole shutdown on success clause. So we could do that, but I don't think it's going to be very interesting because, as we just saw, it was already a very large class file. So yeah, let's talk about that after. What if I want to use a result of two virtual threads as the input for another virtual thread? Is there a new recommended API yet? Ooh. No, I don't think there will be one yet. But maybe with the structured concurrency part, you can have nested scopes. So that could be one of the options, or yeah, probably how you would solve it currently with how you would do it with platform threads. So don't think there will be a recommended API yet. So can we call interrupt on a virtual thread? Yeah, let's see. 1 second was probably gonna be. I don't have to call joins interrupted. Yes, you can. So yeah, it will probably just stop. Sorry? Oh. Ooh. I would. Oh. No, I don't know, because the thread has stopped, so there's nothing to get a result from. So I don't. Yeah. Otherwise, we can just code it right now if you want, or after. That's. Yeah. Wait, what was the question? Because. Okay. So, if there are any more questions, or if you have something specific, then feel free to come to the stage after. Oh, thank you for being here.